Welcome. In this literature review, we will be looking at Nathan Green's article, Comparing and Assessing COVID-19 Tests. The article discusses what people mean when they say COVID testing, the implications of getting COVID-19 tested, and how we should interpret these results on an individual scale as well as a population scale. The main questions that Nathan Green addresses in this paper are the following. Can COVID-19 tests, both active infection and antibody tests, accurately represent an individual and the population prevalence of COVID-19? In terms of population scale, can COVID-19 tests be trusted to inform on making policy decisions such as population prevalence estimates and wider public health decisions? Now we will discuss the data displays and analysis presented in Green's article. In terms of the two COVID tests that are publicly available, namely active infection tests or past infection tests, PCR or polymerase chain reaction tests are used to detect an active infection, whereas antibody tests are used to detect past infections. Here is a summary of the two types of tests we will be observing. PCR, or active infection tests, are molecular tests which give more accurate diagnostic results but are slow to deliver the results to the patient. Antibody tests are serological blood tests, which tend to be less accurate, but they are easier to use and deliver results much quicker. Both tests have imperfect performance. PCR tests depend on the time at which the test is taken. If the patient takes the test too early after being exposed, the PCR test will not pick up the COVID-19 infection. For antibody tests, an incorrect result may be due to identifying patients with a response to other human infections like the common cold. For either test, researchers like Nathan Green should be looking at the sensitivity and specificity to determine the test performance. Nathan Green performed a sensitivity and specificity analysis on each test in observance. Just a reminder that sensitivity is the probability a test will be positive if you actually have the infection. Conversely, the specificity is the probability that a test will be negative if you do not have the infection. The data that is displayed in this paper includes tables listing the sensitivity and specificity in each test in observance. For active infections, metrics for Chorus bioconcept and Novasys Permer design are included. For past infections, tests for SARA-CoV-2, biometrics Rapid, and Roche are included. First, the study split up the population of people requiring tests into 5 pillars. Pillar 1, swab testing in PHE labs and NHS hospitals for those with a medical need and the most critical workers and their families. Pillar 2, swab testing for key workers and households. Pillar 3, mass antibody testing to help determine if people have immunity to coronavirus. Pillar 4, a national surveillance for population blood testing using a high accuracy antibody test operated by Public Health England. Pillar 5, spearheading a diagnostic national effort to build mass testing capability at a completely new scale. After the data was split up into different pillars of populations, Nathan Green came up with calculations to calculate the true prevalence estimate, which are informative in making public health decisions. Then he used the true prevalence estimates to help calculate false positives and false negative probabilities of each type of test. Next, we will go over how these metrics are calculated. The true prevalence estimate is calculated by taking the probability of the positive test result plus the specificity minus 1 and dividing that quantity by the sensitivity plus specificity minus 1. Nathan Green assumed all of the tests reported on the DHSC website used either the Chorus or the Novicis test. Using this above equation, he was able to estimate the true COVID-19 prevalence on a given date. In this study, it was May 1st, 2020, which corresponds to the end of the first wave of COVID-19. False positives and false negatives for high and low prevalence of prior COVID-19 infections are calculated in the following way. False positives is equal to the quantity of 1 minus the prevalence multiplied by 1 minus the specificity. For false negatives, we multiply the prevalence by 1 minus the sensitivity. Nathan Green assumes, with evidence that is not presented in this paper, that a 20% prevalence is high prevalence for COVID-19 infections, and a 5% population prevalence is low prevalence for COVID-19 infections. Nathan Green gathered several informational results from the sensitivity and specificity analysis of the COVID tests in question. We are observing the test positivity and the estimated true prevalence for the Chorus and Novicis Permer design tests. In the article, this information was presented in both a bar plot as well as a table with raw numbers. The bar plot is showing the test results and true prevalence estimates based on the Chorus and Novicis Primer test sensitivity and specificity values for pillars 1 and 2 discussed previously. This plot also depicts the percentage of positive results out of the total number of tests performed. In both pillars 1 and 2, Chorus Bioconcept had estimated more true positives than the observed number of positives, rather than the Novicis Permer design, which estimated slightly few positives than the observed positives. Underestimates of true positive results can severely affect the population prevalence of COVID-19 infection, while overestimates have lingering psychological effects on the patients who are receiving wrongful results, a trade-off in either direction. This outlines the importance of creating the most accurate test for all circumstances. Next, we will discuss the results from the test statistic estimates for the 3 antibody tests being analyzed in this study. Nathan Green made a point to identify that the test counts and prevalence estimates for demonstration purposes only, but they do, however, help us in making useful conclusions about the antibody tests present in the table. The table presents 2 prevalence estimates for each antibody test, namely low prevalence at 5% and high prevalence at 20%. Looking at the raw numbers that are presented in this table can be a little bit hard to comprehend, in addition to increasing the difficulty of making inferences and conclusions about the metrics that are given. For this reason, Nathan Green decided to present the biometrics prevalence estimates in a waterfall plot, which we will show and discuss next. This figure shows the estimated test statistics for the biometomix antibody test with the set level of population prevalence of 5%. This waterfall plot of results for the biometrics antibody test only. The green bars indicate agreement between the observed and the true test results, whereas the red indicate disagreement between the observed and true test results. We can see that the true positive and true negative are in agreement with the observed quantities. On the other hand, false positives and false negatives are in disagreement with the true observed metrics. Overall, the biometrics antibody test is able to predict true positives and true negative COVID-19 results close to the observed results. But when it comes down to false positives and false negatives, we do see a disagreement between the observed values. Antibody tests give us information on how much of our population is immune to COVID-19. So having slightly skewed results from this test will affect public health decisions. However, it will not affect the overall population prevalence of COVID-19. We are hopeful that the disagreements are much smaller quantities than the agreements in the observed test. This allows us to make meaningful conclusions from the antibody test in question. Up next, Nathan Green's key results gathered from the sensitivity and specificity analysis. The information provided about the test is often unclear or missing. Nathan Green aimed to clear the air surrounding COVID testing with his analysis. He did recognize values can vary widely between tests, and individual test statistics themselves have huge uncertainty. Thus, the test numbers used in this study are for demonstration purposes only and have been selected to be the most representative of May 1st, 2020. For active infections, Chorus Bioconcept had overall sensitivity of 60% with specificity of 100%. Novasys Permer Design has sensitivity of 88.6% and specificity of 90.6%. For past infections, Q-SARS has specificity of 95.6% and sensitivity of 93.8%. Biometomix has sensitivity of 88.7% and specificity of 90%. And Roche claimed to have sensitivity of 100% and specificity of 99.8%. Next, we will discuss the remaining challenges that proceed over COVID-19 testing. Considering the age that we live in, we need to consider the remaining challenges that are present with COVID-19 testing as we head forward into the future. New, more reliable tests are being developed, which creates a new issue of determining which tests are the most reliable on the specificity and sensitivity levels. We would need researchers along with statisticians to conduct overarching sensitivity and specificity analysis for all the developed tests in order to determine which tests are the most accurate and most reliable. The population prevalence scale of accuracy is good and well represented by the way of tests, but how can we have more confident, reliable predictions on the individual scale when taking the COVID-19 antibody and active infection tests? This is a question of high importance because making incorrect predictions on an individual scale can severely affect how much COVID-19 is prevailing on the population scale. Although there are remaining challenges to decipher the accuracy and reliability of the COVID-19 tests, Nathan Green was able to make meaningful conclusions which had significant impact on the COVID-19 testing topic. Green's work will have lasting effects on the future of COVID-19 tests. His research was conducted for the first wave of COVID-19 and hence could be applied to current COVID-19 tests that have since been developed. He concluded COVID-19 testing is not perfect. They are only attempting to make it better and more accurate. With more tests being developed, researchers will be able to make more concrete conclusions about the sensitivity and specificity of each test in order to determine the best. Incorrectly ruling someone as having COVID-19 can have serious psychological and financial impacts on the patient in question. Incorrectly ruling someone as not having COVID-19 can have serious population impacts, such as mass spreading and ignorance to their own COVID-19 status. In the current state of the country and the world, COVID-19 testing is of huge interest, so it is likely to get more accurate and more representative of the true observed COVID-19 infection on both the individual scale as well as the population scale. Nathan Green has spearheaded research of COVID-19 tests and will continue to examine the reliability and accuracy of the active infection test as well as the past infection tests. Thank you.